Thank you for taking the time to view my presentation today. My name is Zach, and my question for you to ponder is, will temperature affect the flow rate in your home pipes if the water contains impurities? Hypothesis. You may be forming your own hypothesis, but it was my hypothesis that if impurities were present in drinking water, then the flow rate or viscosity of the drinking water would change with temperature. Background. So why would water contain impurities? Well, before entering our home, water travels over the ground, rocks, and soil, dissolving substances on its journey to wells and reservoirs. The National Institute of Health reports that adults can expect to find daily values of up to 16% for magnesium, 31% for calcium, and 5% for sodium in every 2 liters of drinking water. Now, the presence of calcium and magnesium will turn water hard and tend to build up, leaving a film that can ruin a bathtub or, in our case, damage a pipe. The presence of sodium, conversely, should create the opposite, soft water, which may be equally capable of harming pipes or slowing flow rates. As a result, I decided that I want to use my knowledge of physics to take a closer examination of flow rate on hard and soft water. Analyzing flow rate would allow me to test forces of friction within the fluid under various conditions, including temperature. Friction reduces mechanical energy and therefore should slow moving water in a pipe by my hypothesis. Materials. Here are a few of the materials you may need to repeat this experiment, including purified water, powdered magnesium, calcium, and sodium, along with some typical lab equipment. Procedure. Now, I began by creating a solution of magnesium, calcium, and sodium to represent the typical impurities found in drinking water, and used a burette to properly measure and represent my pipe. Using a stopwatch, I recorded the time it took for precisely 40 milliliters of the solution to flow. I then created a flow rate using the volume divided by time. I went on to repeat these steps for water at room temperature, near freezing, and piping hot, no pun intended. I also tested a separate hard water solution and a separate soft water solution at various temperatures. Finally, I was sure to test purified controls. Summarizing results. Summarizing my results on this page, you will see that in all trials, including the control, water at the highest temperature of 115 degrees had the greatest flow, while trials at the lowest temperatures of 38 degrees had the slowest flow. The green and blue bars in the graph best indicate this. Comparing results to the control. Now on this page, I have compared my results to the respective control. Whether the impurity was hard or soft, they all appeared primarily slower than the comparative control, with the one exception of my red arrow. This is the combined hard and soft mixture at high temperature, and of interest, you might note this is also how many home water softening filters work. They reverse or balance hard water with the addition of salts, indicating their possible effectiveness. Comparing results to the control. And the final graph on this page shows the comparison to the control on a percentage basis. This may indicate more general changes of flow rate as impurities and temperatures change in a pipe. A 2% change seems small, but long-term may be of more interest. Conclusion. In concluding, the solubility of impurities at various temperatures can change flow rate. One possible explanation for the changing flow rates is that the solubility of solid impurities typically improves with increases in temperatures and lowers friction, while the reverse is also true. 85% of homes in the U.S. may have hard water, and although the NIH has reported these impurities are of little concern for healthy individuals, they may not be so healthy for your home pipes, especially over the long term. I therefore recommend, after testing your water, you consider consulting a solubility curve to know how these impurities may dissolve and change your flow rate at various temperatures. Error improvements. Finally, on this page, you will note that I have attempted to eliminate experimental errors by repeating trials and measuring appropriately with a digital scale. Also, extensions on this project may prove useful over longer time frames, while testing additional impurities such as the presence of iron on flow rate may also be interesting in future edition. Here you can see my works cited. Thank you for your time today. I hope you enjoyed this presentation.